Welcome to part 3 of 3.1. Here we're going to be connecting a function and its derivative graphically and algebraically. These are not necessarily strict examples of how to do some exact skill, and so instead of calling these examples, I'm going to call them explorations. The first function that we're going to explore is f of x equals negative the quantity x plus 3 squared. Now this is a quadratic function, and it will make a parabola that opens down because of the negative. But I'm actually going to just expand this instead, so it's a little bit easier to work with. So if I expand the x plus 3, all of x squared and plus 6x and then plus 9, and then distributing the negative through, everything will end up actually being negative. And this one might be a little simpler to deal with algebraically if we need to plug in x plus h, which we will shortly. When we take a look on Desmos, we can see that this clearly is a parabola and it's opening down. We also notice that the function is increasing from when x is negative infinity until when x is negative 3, and that our function is decreasing to the right of negative 3 when x is negative 3. Therefore, we can just write a couple things about the function and its derivative, kind of splitting at negative 3 here. So I'll use red for the original function, f. And we can see that over here to the left of x equals negative 3, f is increasing. And to the right of x is negative 3, f is decreasing. And what we can do is sort of put like a little dashed line through x is negative 3 just to show kind of the split. Now, when our function increases, that means that the derivative values are positive. Remember, the derivative is the slope of any tangent line that we would draw. When f is increasing, that means the values of f prime, the derivative, are positive. And when f is decreasing, that means the values of f prime are negative. At that turning point when x is negative 3, it's an interesting idea because if we were to draw the tangent line here at this vertex, the tangent line would be horizontal. The slope of any horizontal tangent line or any horizontal line is 0, and therefore at the point when x is exactly negative 3, that is when f prime equals 0. Now so far what we've done is we have sketched f prime based on some values of the derivative, the slopes of different tangent lines that we've either drawn in, estimated, or that I have given you. At this point, what we're going to do is algebraically find the equation of the derivative and then actually graph it on Desmos on this same screen. And then that way we can compare and make sure that everything works out. Let's find f prime using algebraic methods. So f prime of x is the limit as h goes to 0 of f of x plus h minus f of x all over h. And we will use the f of x that is right here, expanded. So we need to plug in x plus h into both spots where x is. This is something that a few students missed on the last two assignments ago. And when x is represented in the function once, more than once, 3 times, whatever, we have to plug in x plus h to all of those values of x, not just the first one. So we need to have a negative out front, and then square x plus h, subtract 6 times the quantity of x plus h, then minus 9. So far I've written out f of x plus h. Then we need to subtract f of x, and when we subtract something with more than one term, we need parentheses to ensure that we distribute the negative sign correctly. In this next step, we first need to square x plus h and then distribute the negative through to those 3 terms. I'm going to do that in one single step because we've squared x plus h enough times now. We understand the 3 terms we get are x squared, 2xh, and h squared, and now they are all negative because of that negative out front. Then we'll distribute the negative 6 through and a minus 9. Then we distribute the minus sign through all three of these negative terms, turning them all positive. Now at this point, when everything's been expanded, every term that does not have an h in it needs to cancel. If that's not the case, then you did some sort of algebra wrong. We have a negative x squared and a positive x squared, a negative 6x and its opposite, and a negative 9 and a positive 9. All the terms that are remaining have h in them, which is correct. When we factor this h out, we should have 3 terms inside the parentheses, is because we have 3 terms with h in it still. So we need to represent all of those. Here we're left with a minus 2x, here we're left with a minus h, and here a minus 6. And now we can successfully cancel, and so now we can direct substitute 0 in for h. This middle term goes to 0, and we are left with that f prime of x equals negative 2x minus 6. That is a linear function. It's going to make a line. Let's graph that on the same graph that our original function f of x was on. So here we can see the original function f in red, and then f prime, the linear function that we just found, graphed in blue. And I'm going to write a couple things on here. Over to the right, we can clearly see that f was decreasing over here, and therefore our derivative is negative. It is below the x-axis. Its output values are negative. To the left of when x is negative 3, our function, original function f, is increasing, and therefore its derivative lies up here. It is positive. When we have the turning point on f, meaning the function goes from increase to decrease, the function has a derivative there of 0 because the tangent line drawn when x is negative 3 would be horizontal and therefore have a slope of 0. So to write in just those couple points that we made, to the left of when x is negative 3, our original function was increasing, and to the right, our original function was decreasing. That means when the function is increasing, that means that the derivative, and I'll write that actually up top, the derivative was positive, greater than 0. We can see that it literally had positive y values to the left of when x is negative 3. To the right of when x is negative 3, our function was decreasing, and therefore the derivative lived below the x-axis. It was negative. When x is negative 3, here, at this point, the derivative was 0 because f was neither increasing nor decreasing there. In this next exploration, we take a look at f equals x cubed, which is in red, and then we have already, I'm being so lazy, I've done this a few times, we have already noted that the derivative of x cubed is 3x squared. It takes a while to cube the whole x plus h thing, so we are just going to go with we did it once and we're good. So let's take a look at these two graphs here. I maneuvered a few things around here. We do note that f, the original function, is cubic, and therefore its first derivative, f prime, is one fewer degree, meaning it is x squared, it's quadratic. We actually saw in the previous example that when our original function was a quadratic, a parabola, its first derivative, f prime, was linear. So it goes down by 1 degree or 1 exponent. And so let's take a look at how the graph of f is increasing or decreasing and how that affects our derivative. We do note that all along here, the graph of f in red, x cubed, is increasing. It increases until it hits 0, where it levels off. However, it does not begin to decrease. It continues increasing. So the graph of f, our original function, is either increasing or just stagnant for a moment when x is 0. It is never decreasing. Therefore, because it's never decreasing, f prime, the derivative, is never negative. It's always positive or 0. Now we can see here that as we go more left and as we would go down, if we were to draw tangent lines here, they would be incredibly steep. And then they would begin to level off, get less steep until they hit 0. I can sketch those here in black. We would have a very steep tangent line, a less steep one, a less steep, until we hit a horizontal tangent line right here when x is 0. And note that the slopes of all of those lines are positive, but they're ever closer getting to 0 as x goes to 0. And so we can see that f prime, the values are very large negative numbers, but then the derivative, just like these slopes here, what the derivative is measuring, goes closer to 0 until the derivative is 0. Then the derivative stays positive and gets higher and higher and higher, larger numbers. If we look to the right here, what is our original function doing? The tangent lines that we could draw here would be, the slope would have a pretty small positive number, and then the tangent lines get steeper and steeper, meaning their slopes would be larger positive numbers. So we can clearly see that since f is increasing here, and then f is increasing here, and here f is neither increasing nor is it decreasing. That's like a turning point. We can see what happens with our derivative in those spots. Here, our derivative is positive. Here, our derivative is equal to 0. And here, on this side, our derivative is positive again. When the original function is increasing, the derivative is positive. And when the original function is neither increasing nor decreasing, it's flat, it would have a horizontal tangent, that means the derivative is 0. Because our original function never is decreasing, our derivative, f prime, is never negative. Our third and final exploration is just of a linear function, f of x equals negative 2x plus 5. I want to algebraically find f prime. And again, we'll do that by finding the limit as h approaches 0 of f of x plus h minus f of x all over h. So the first thing we're going to do is find f of x plus h, which is that. Then we'll subtract f of x, which is negative 2x plus 5 all over h. Because this function is just linear, there's not really a ton of algebra to really do. We just have to be careful that we distribute negatives correctly. And again, everything without an h should end up canceling, which it does. We see that the negative 2x and positive 2x cancel, as well as the 5 and the negative 5. Then we're actually left with something that doesn't necessarily even need to factor. It will just cancel because it was down to one term. So that means that f prime here doesn't even have an x in it. It's just negative 2. Well, that makes sense. If we think about this line, our original f of x, it's linear, meaning it has a constant slope. The rise over run is always negative 2. The slope never changes. In fact, it's just our m value. And we see that no matter where we are on that line, our slope is constant. It's always negative 2. So let's graph those together. We can see here that our original function is in red, y equals negative 2x plus 5, and then our derivative is in black. It is just a constant. A linear function has a constant derivative because it never changes. This rate of change, no matter what x value we're at, is always the same. It's always negative 2. We can't even really draw a tangent line. It would just be this line. The tangent line would, no matter where we are, would always have the same slope, and that would be negative 2. So lines are something that we learn about early in mathematics, like in Algebra 1 or even in 8th grade, because it's an easy idea to understand that a slope can be constant throughout. When we get to higher order polynomials like quadratics, cubics, quartic functions, where we have exponents other than 1 attached to our x, that is when the rate of change changes. In this case, with a linear function, the rate of change is constant. this last slide here, these are just some of the main ideas that we've talked about today. I'm just putting them down into words. This is something I wrote on in another video, but if we have like a linear function, its derivative f prime would be a constant. That was just shown in exploration number 3, where we had f of x equals negative 2x plus 5, and its derivative was just negative 2. When we had a quadratic, that was shown in exploration number 1. Its derivative was a line, linear, not a horizontal line, an oblique line. And then if a function is cubic, which is shown in our middle exploration, its derivative was quadratic. We could just keep going. Basically, whatever your degree is, so linear is degree 1, constant's degree 0. A quadratic is degree 2 because it's x squared. Its derivative goes down to degree 1, a linear function. Cubic is degree 3, x cubed. Its derivative is 1 less, x squared, and so on. Quartic means x to the 4th. Its derivative would be cubic. We could go on infinitely. Another main idea is that how f of x behaves on some interval determines what your derivative looks like graphically. So if f of x is increasing, that means the tangent lines would all have positive slopes. Therefore, the derivative would be positive. If f of x is decreasing, it just means the opposite. The tangent lines drawn on that interval would have negative slopes, therefore the derivative would be negative. And if f of x is neither increasing nor decreasing, that can look like 2 different things here. It can look like, or 3 different things. It can look like a maximum point where we're neither increasing nor decreasing, a minimum point where we're neither increasing nor decreasing, or kind of like a stagnant point, like in a cubic function, where we go from increase to increase as well. So, or decrease and more decrease, like another stagnant point. So it can look like those 4 things. Basically, if your function at a certain point is neither increasing nor is it decreasing, that means that the derivative is 0 because it would have a horizontal tangent line. All right, I hope that video gave some good explorations for connecting a function f and its derivative f prime.